These are three night view pictures of the highest populated cities on Earth. The first is Seoul, second New York, and the last one Singapore. What commonalities can you notice about them? Well, all of them are brightly illuminated during the night. Well, city lights are indeed beautiful to look at. What if we told you that this extravagance can come at a cost? At a global scale, light is used increasing rapidly as more countries undergo urbanization and development. Artificial light is one of the hallmarks of the modern world today. It is the quintessential lifeblood of any urban city, and it enables its inhabitants to function beyond natural light hours. However, it is not without its drawbacks. The use of artificial light inevitably leads to light pollution, which can have a significant impact on our climate. As the global trend of urbanization continues, and a strong corresponding increase in the use of artificial light, we will need to be able to monitor and understand the impact our city lights have on the climate. Today, we will be focusing on the darker side of city lights, and we present our satellite project EclipseSAT. It will serve to measure and monitor city lights and its impact on climate change. I will be presenting the concept relevance of our mission, Mingchuan, the mission parameter, Ern Tze and Jin, the technical characteristics, and the budget. Light pollution is able to affect the climate directly and indirectly. Artificial light sources, especially those that are less efficient like low-power sodium street lamps, are able to have an overall 50% influence on air temperature according to a geographical weighted regression. This could lead to warmer climates in general and earlier spring for places with higher latitudes. Furthermore, the glare of lights interfere with chemical reactions that cleans the air pollution during the day, and by night, up to a 7% increase in chemicals that produce ozone pollution during the day as much as 5%. These leave higher levels of air pollution, which will trap heat that exacerbate global warming. A more indirect way that light pollution leads to climate change is through energy waste. Global light emission constitutes to about 46,000 gigawatts of energy. Moreover, International Dark Association published an estimation that the energy consumption and wastage due to light pollution shows about 9 million tons of coal and 32 million barrels of oil wastage. This has resulted to a wastage of 1.74 billion of energy resources each year. From our research, we found that different street lamps will have different characteristic wavelength, which can be used to identify the composition of the overall light measured through EclipseSAT, as seen from the figure. Through monitoring and tracking heat signatures from the city, EclipseSAT mission will be able to catalog more energy-efficient lighting with the lowest impact on temperature. It will also serve to understand how different city models with different type of city lighting can be better used with new technology and more efficient phosphorus converting amber street lamps and light emitting diode street lamps to recommend an optimal region to employ them. We aim to utilize EclipseSAT to measure regional light pollution of urban cities and develop an analysis of seasonal or transitional changes in light usage to inform urban policy. We also aim to use EclipseSAT to monitor the types of light that the cities are using and its impact on the environment, such as additional heat release and energy wastage. And we also want to use them to encourage cities to switch to more efficient street lighting systems.
Hi, my name is Mingchuan, and I'll be talking about orbital parameters of our satellite. So let's take a look at orbital parameters. So the orbital type we have chosen is the sun-synchronous circular orbit. This is so that it can cover most of the cities in the world with no problem. It also has a mission lifespan of 2 years, such that giving it enough time to cover majority of cities that we want to analyze on. It also has an orbital height of 800 km, and at this altitude, we will have an orbital period of 101.3 minutes and orbital velocity of 7.45 km per second. In addition, its orbital inclination is 97.8 degrees since it's a sun-synchronous orbit. So this is what happens when it's in the orbit. So this is reference its own orbital plane, a circular plane. So at this orbit, will have an eclipse time of about 35 minutes. So it spends about 35 minutes in the shadow of Earth, while the rest of the time during each orbit, it will be under the sun. So when it's under the sun, our CubeSat, EclipseSat, will turn its solar panels using ADCS system such that it will be sun facing. And after that, once it's in a shadow, it will use the ADCS system and turn around such that the payloads will be facing the ground such that it can do its mission. Also, we have a daily average time above the ground station about 770 seconds. This is taken over a period of a month, averaging it out. So the ground station I've chosen is CRISP, which we will talk more about it later. So let's take a look at the simulation that we have. So this is the orbit, and this you can see is the ground station, CRISP. Let's take a look again. This is CRISP, located in Singapore. Okay, next let's take a look at mechanical characteristics. So let's take a look at our payload that we have. So we have 3 payloads. The first one is the spectrometer, which is used to analyze the different kind of light spectrum that the city lights emit. Next, we have an optical camera, so that you can tell how bright the city is. And also having a visual confirmation of what we are looking at is correct or not. Next, we also have an infrared camera, which will tell us more about the heat signature of our city that is the heat that the city is generating through the heat signature. So let's take a look at system architecture and how everything is placed inside. So we have chosen it to be a 12-unit CubeSat, which is a 2x2x4 height. So this is how everything looks like inside, with our payload at the front, at the top over here, and the battery system in the middle, ADCS system below that, and after that we have our solar panels and everything at the side. So this is the view after we have moved all the plates that is protecting the satellite itself. Okay, so this is how it looks like when it's closed up and open up. So on the left, when it's open up, from the bottom, we have our solar panels, we have the sun sensor and the star sensor, such that give us the accuracy we need for our ADCS system in order for it to able to target a city and keep track of it. On the right, we have it being closed up when it's about during launch. Yeah, as you can see behind the solar panels, there are the shielding and also the different kind of layers to protect it from heat and also from impact. Yeah. Okay. So this is how it looks like. It's a 12-unit and dimension is such as this in mm. It has a gram of about 22,000, which is about 22 kg. And its CG is about 120 mm, 116 mm, and 129 mm. So what it translates to is such that it's roughly about halfway in the middle, and slightly is about 129 mm above the bottom. So this is roughly where our ADCS system is. Yeah, so this will able to maximize the ADCS control such that the least amount of angular momentum is needed in order to turn the satellite. Next, the deployment system, we have chosen a veteran tie-down cord made of UV degradable material and the nichrome burn wire in order for our solar panels to be launched. So what happens is that once in a space, right, the nichrome burn wire will be lit up and its temperature will be very high such that it will melt the tie-down cord. Yeah, and after that, once the tie-down cord is melted, right, our solar panels will spring into action such that it will start collecting energy and everything else in the system will start working. However, in the case that our nichrome burn wire fails to work somehow, our veteran tie-down cord is still made of UV degradable material. This is so that after a while, when it's exposed to the UV light ray from the sun, it will be able to melt itself and degrade itself such that our solar panel will be launched no matter what. Yeah. Okay, so next, I'll pass my time on to next person, Ern Tze, to talk about more about our ADCS system.
Hi, I'm Ern Tze, and here I'll bring you all through the ADCS subsystem of the EclipseSAT. In order to achieve our mission objective, the EclipseSAT is required to determine during launch, be able to orientate itself to face the Sun or Earth, perform attitude control and stabilization, as well as identify key city locations. As such, an active ADCS system is needed, and the Cube ADCS and PNAV and GPS will be used for ADCS of our CubeSat. Cube ADCS is an integrated ADCS system from CubeSpace, which consists of several ADCS modules, such as Star Tracker, Horizon Sensor, Sun Sensor, and Magnetometer. It also consists of 3 reaction wheels and a magnetic torque coil as actuators for the ADCS. This will enable EclipseSAT to perform 3-axis pointing, detumbling, and stabilization of the CubeSat, as well as perform various pitch maneuvers. Next here, we have the PNAV and GPS. It is a small-sized GPS which will be used alongside our Cube ADCS to allow us to determine city locations in order to provide a more accurate attitude determination of the EclipseSAT. For the onboard computer of EclipseSAT, we will be using the ISC onboard computer. The ISC OBC is capable of temperature sensing and has a USB interface for our spectrometer. It is also compatible with our CubeSat frame and the EPS system. It has two 2GB SD card to store our payload data, which we calculated to be 22.45 GB, which will be generated daily. Next here is the thermal control system of the EclipseSAT. It uses an active heating and a passive cooling system to keep the EclipseSAT at its optimal temperature. For the passive cooling system, there will be heat sinks placed at the solar panels in conjunction with heat pipes. For heating, we will be using thermal foils to actively heat up the CubeSat during eclipse phase. Moving on to power budget of the EclipseSAT, we calculated the power required by the CubeSat at the sunlight and eclipse phase at the worst case scenario, and calculated a total energy required of 62 watt-hours. On the right here is the power budget of the various subsystems. This is the power budget of the Cube ADCS, which was used in the power calculations earlier. For the solar panels, we will be using the ISC CubeSAT solar panels. From our calculations, power required by our solar panels is 67.3 watts, as each 6 new solar panels will give 70 watts of power. We will employ 4 6U solar panels to generate a total of 68 watts, which will be sufficient to power our EclipseSAT. We will be using the ISC modular EPS to store, regulate, and distribute power to the CubeSat. The EPS consists of a battery pack, conditioning unit, battery unit, and a distribution unit. For its battery sizing, we calculated that EclipseSAT requires 8 ampere-hours of power. Accounting for a safety factor of 4 to ensure sufficient battery capacity for our mission, we will be using 12 battery packs, which will provide 34 ampere-hours of power. I will now be passing the time over to Jin, who will be sharing about the TT&C subsystem of the EclipseSAT.
The TT&C that we have chosen is CubeSat antenna system for 6U or 12U and VHF uplink, UHF downlink full duplex transceiver by ISIS. We have chosen these systems as it has a deployable antenna compatible with ISIS frame and low power consumption. The total data transmitted per day is calculated to be 0.9336 megabytes. Now I'll introduce the budget part of our satellite project. Our satellite is interfaced by 12C. This is the electronic diagram of our satellite. This is the command and data handling of our satellite. It shows how the onboard computer will position the satellite. When our satellite is under the sun, it would turn it to face the solar panels to the sun. When our satellite is above the target city, it would face the payloads to face the city. When our satellite is above the ground station, it would turn to point antennas to the ground station. This is how the satellite would behave during the day. And this is how it would behave during the night. To check distribution of light in the selected cities, we have used 3 payloads: spectrometer, thermal camera, and optical camera. Since we have 14 orbits per day, we decided to collect 1,400 photos from spectrometer, 700 photos from thermal camera, and 70 photos from optical camera. We decided the number of photos considering the significance of the data to our mission. After compression, total data downlink size is about 10.7 megabytes per day. Transmitting this amount of data would take about 371 seconds, which is within 778 seconds, our satellite's average time connected to our ground station. This is the free space loss equation. Given that our maximum distance of transmission is 1,770 kilometers, the calculated free space loss is about 150 decibels. The left table shows the transmitter from ground station to our satellite. The transceiver on EclipseSAT has a sensitivity of minus 104 decibel meters. Since we can always increase the power of our ground station, we can vary the transmitter power. As long as the transmitting power is more than 56.23 decibel meters, EclipseSAT would be able to receive the signal. The right table shows the transmission from satellite to the ground station. Assuming that the temperature is 293 kelvins and bandwidth is 438 megahertz, we will get a noise floor of minus 87.51 decibel meters. Given that a typical ground station with a satellite dish of size 15 meters to 30 meters will have a receiver gain of 60 decibels to 65 decibels, we assume that CRISP, with a satellite dish size of 13 meters, will have a receiver gain of about 55 decibels. This will give us a receiving power of minus 78.23 decibel meters. This is more than 3 decibel above the noise floor, and thus the ground station will be able to receive the signal from the satellite. This is our estimated cost to build the satellite. The total estimated cost is about $1,430,000 US. We aim to earn this money by getting sponsorship from organizations such as International Dark Sky Association and the regional municipality. Thank you for listening to our project.